Good morning. My name is John Belkwitz. I'm co-founder and president of Eddystone, where we specialize in concrete antibiotics. Today we're going to explore the remarkable innovation in the field of concrete repair that leverages the unique properties of colloidal silica hydrogels to create a phenomenon known as crack blunting in cracked and deteriorated concrete. Now, by blunting cracks in cracked and deteriorated concrete, the resiliency to crack propagation or the continuation of cracking in concrete is reduced. Now, this presentation aims to provide a comprehensive understanding for civil engineers, material scientists, and asset managers on how hydrogels like these can be used to extend the life and enhance the durability of cracked concrete structures. Now, before we get into the meat of the presentation, I'd like to give you an overview of where we intend to take you on this journey. All right, on to the overview. Now, first and foremost, we're going to start out with the purpose of the presentation. Part of this will include the background on our essential and primary objectives. From there, we'll review concrete cracks and the mechanics of crack propagation. These will act as the foundation for our presentation that we'll build on for the impact of these hydrogels. And finally, that final big ticket walk-away item is crack blunting with colloidal silica-based hydrogels. Here, we're going to cover the chemical and physical interactions and reactions that the hydrogels have with the walls at the crack concrete and pore water solution interface to bridge concrete cracks, change the geometry of these cracks, and ultimately impact the transfer and distribution of stresses that would have caused concrete crack propagation. On to the presentation. Now, our first top is the purpose and objectives, and this is where we really hang our hat on what you're going to get away from this presentation and the references that you can go back to. Now, the purpose of the presentation is identifying the employment of these hydrogels within concrete structures to mitigate the effects of crack propagation. A common yet significant issue that compromises the structural integrity and longevity of concrete. Now, I'm diving into a book now by Jonathan Walden called Rust, which goes over the greatest war that we have as a global effort, and that's the war that we have against rust and the resources that go to it every year. When it comes down to concrete, which the author refers to it as the cancer of concrete, and I love how people use that term, cancer of concrete, for so many different problems in the concrete industry. But it's not just them. The Portland Cement Association accounts the premature failure of concrete structure in infrastructure is primarily due to the failure of the steel reinforcing system. So what we're ultimately looking at is how can hydrogels create an environment to blunt these cracks, this process to increase the resiliency of already deteriorated concrete. Okay, now on to the objectives, because there's a lot to talk about here. There's a lot to unwrap. All right. Our objectives include the following. First, it's concrete crack review. The first thing that I want to do before I get into the mechanics of concrete cracks is I want to define what a concrete crack looks like and the geometry. Now, I do this twofold. One, I take the crack that we have in front of us. This is a piece of concrete with a cracked concrete section with a classic wedge that we associate with a piece of concrete that has cracked. I want to define the certain sections of it. And then I want to look at the life cycle that concrete goes through, not only to develop this type of crack, but the exacerbation of this crack that ultimately leads to a compromise of the cover for our reinforcing steel, or sometimes even the structural capacity of our structure and infrastructure. Okay, so after that, we're going to go into the mechanics of crack propagation. Now, this is looking at the different parts of a concrete crack and how that concrete crack continues based on the geometry and the transfer of loads and stresses from the concrete structure to the concrete crack. And it's important to understand that, because that is that foundation that we're building on. That is what we want to take control over to limit further deterioration of the concrete. Now, that is our final objective here, which is examining the role of hydrogels to achieve this crack blunting and consequently aiding in that concrete repair, that reclamation, that return of some type of resiliency to the nastiness that we often get with our concrete environment. And what we're going to do is go through the hydrogel development, which we oftentimes do, and in some cases for our return visitors or our return listeners, this is going to be a little bit of a broken record. But what that's going to allow us to do is get into the chemical and physical phenomena of crack blunting and how the hydrogel impacts that and the properties of our concrete. Now, while we will be getting into some basic information, this is going to be very heavy on the technical side of mechanics of materials as well as material science. Now, my expectation is that you, the audience, that you've done a little bit of homework on this subject. At times, I have been told that I sound like, or I might sound like, a physics professor that starts the first day of class on chapter 9. And the unfortunate reality is I might be doing that because there are certain subjects that I expect you to have gone through before reading this, or at the very least pausing it, cracking open a Wikipedia or maybe some other YouTube channels to get into some of these other concepts and phenomena that I'm talking about. So without any further ado, let's get into it. All right, so our next topic is concrete crack review. Now, this is extremely important. There are some great textbooks out there that go into the mechanics as well as the geometry of cracks in more detail. My favorite book and author is Engineering Materials 1 by Michael Ashby, and I believe it's chapter 5. We'll include a link to that textbook in the description below. Concrete cracks occur to various reasons, including thermal expansion and contraction, shrinkage, stress concentrations, external loads, and more. These concrete cracks not only impact the aesthetic value of structures, but also significantly reduce the service life and safety of concrete. Crack propagation in concrete follows a very specific mechanism and path where the stress intensity at the crack tip exceeds the material's toughness. Now, we're going to go into this in more detail later. This phenomena results in the extension of the crack, further compromising the structure's integrity. Understanding the mechanisms behind this allows engineers, architects, and even contractors alike to develop strategies to inhibit or slow down concrete crack growth. The first thing that we need to do is define the strategy, the geometry behind a concrete crack. Now, a crack is broken down into the following. The first is this length of crack A, which is the distance from the surface of the concrete down to the crack tip and the wedge in between. Now, this is where we have either a loss in material or where the material is compromised and it doesn't have the same properties as the parent material. Now, behind that crack tip is this plastic zone of the crack, where the crack is going to start to develop. And the important term is the plastic zone, because this material has already gone through some premature failure. It is not the elastic side of concrete, where the term elastic assumes that the material can deform and go back to its original material, original form. That is the term elastic properties. Now, in the plastic zone, where we've already gone through some initial failure, when it goes through any failure after this point, the material will deform and not go back to its original state, or it will lead into failure, increasing the crack size until the crack grows and the strained material behind the crack tip unloads, and we increase the length of crack A. Going a little bit further into this geometry, from the surface of our wedge to our crack tip, we have this change in diameter. Our diameter, we're going to assume, based on this crack geometry, is going to get smaller. So D1 is larger than D2, D3, D4. Furthermore, a crack is broken down, as we said, into the following. Our crack length A, where we have this loss in material, and then behind the crack tip, we have this plastic zone that develops at the crack tip. Now, as the applied load increases, the plastic zone increases in size until the crack grows and the elastically strained material unloads, leading to that greater crack tip or that greater crack size. Now you see, crack propagation in concrete follows a very specific critical path and certain mechanisms where the stress intensity at the crack tip exceeds the material's toughness. Now, this phenomenon results in the extension of the crack, further compromising the structure's integrity. Understanding the mechanic behind this allows engineers to develop strategies to inhibit or slow down concrete crack growth. Now, first we defined the concrete crack, the crack length with the loss of material, the plastic zone, the applied load, how it increases, and we're going to go more into this geometry and how the load gets intensified, the stress gets intensified at the crack tip. But I wanted to take a moment and break down the life cycle of a concrete crack. The image shown gives you a rudimentary understanding of the concrete crack and what mechanisms cause it to propagate or continue to crack. Now, we grow up in the concrete construction industry understanding that concrete is a porous material and that inherently it develops cracks from the inception, from the progeneration, due to autogenous chemical, plastic, and drying shrinkage. Now, these starting off cracks are only exacerbated by environmental conditions and day-to-day use. Wetting and drying not only causes volume changes, but the contaminants left behind lead to both physical and chemical attack that compromise concrete cracking, and more. Now, if we assume that we're dealing with the concrete crack pictured in the slide, we have our concrete pores that are dry and open to the elements. It rains, it snows, de-icing salts, waves crash, and we have concrete pores that are now filled with water as well as contaminants. Now, that water evaporates and we go back to state number one, albeit now we've had some volume change and probably some more cracking, and we've left some contaminants. Now we go into stage three, where over time, this wetting and drying and leaving contaminants behind leads to cracks, durability issues from chemical attack, as well as this physical attack, and eventually this structural failure. So here we've got this picture of a rudimentary crack we started out with, and has an open crack length of A and a plastic zone ahead of the crack R. When stress is applied to the concrete structure, so on either side of the concrete crack, the stresses or sigma applied is transferred through the concrete structure to the crack location. Now, bear in mind, the way we determine stress is fairly easy. It's, pound force applied divided by the area over which the force is applied. So it's force over area. Now, since force is in the denominator, the larger our area, since area is in the denominator, the larger our area, the smaller the stress. Now, the smaller the area, that means our stress kind of increases fairly quickly. So if our area applied the force, the site is bigger, we will get a small in the area. As it turns out, the area at that crack tip is so freaking small. And because it's extremely small in the denominator, let's say the force is a 4, and our original area was 1 for no other reason than the math is easier. 4 divided by 1 is 4. But let's say we, the crack tip or the concrete cracks, and our crack tip goes from 1 to 0.1. Now, 4 divided by 0.1 is 40. Now, if we make the crack tip even smaller, 0.01, 4 divided by 0.01 is 400. So the smaller you make that crack tip, smaller you make that area, the larger stress becomes. Now, what happens is this transferred stress, this sigma local at the crack tip, becomes huge. There's supposed to be a slick transition there. The localized stress is high enough to overcome the tensile stress capacity of the concrete, specifically the hydrated cement matrix. And this causes cracks to continue to crack. In some cases, the localized stress is so great and the internal crack energy is so awesome that it splits bonds between the chemical composition of our hydrated cement matrix, the atomic bonds of concrete backbone, the calcium silicate hydrate, and it rips apart atomic sheets. And in material science, we call that type of failure cleavage. So now, if we expand the math of this just a little bit, we find that the localized stress, the stress at the crack tip, is calculated by applying a correction factor multiplied to the stress based on the geometry, and then it added back to the original applied stress. This means that the localized stress will consistently be greater than the applied stress unless we can control that geometry. And that is what is great about this. We understand the mechanics. We understand the geometry. We understand the physics and chemistry of the concrete cracks, the contaminants, and colloidal silica. This tees us up a great foundation for us to crush this concept down the fairway. And the equation is right there. Sigma applied plus sigma applied times the square root of our crack length over 2 times the length of our plastic zone. Now, introducing the star of our show, hydrogels. Now, specifically, we're talking about colloidal silica or nanosilica based hydrogels. I assume the same concept can be extended to any hydrogel that has a positive impact on concrete or the hydrated cement matrix. Hydrogels are polymeric materials capable of absorbing substantial amounts of waters, bridging open space without dissolving. Colloidal silica-based hydrogels, which we're talking about today, will bridge the concrete cracks mechanically and chemically, anchoring into the interfacial zone between the concrete crack and the open space. This bridging material acts as a tortuous media for harmful ion transport and a reclamation of concrete resiliency to crack propagation. This unique property is what we harness for crack blunting in concrete. Now, before we get into this phenomena, I believe that a definition of crack blunting is warranted. And crack blunting is recognized as the mitigation effect of stress concentrations caused by cracks. The stress is distributed perpendicular to the crack or in a radial direction, blunting the energy that would increase the crack length. When introduced into the crack and deteriorated concrete through a simple spray-on application, our colloidal silica technology permeates and rejuvenates corroded concrete infrastructure. The nanotechnology accesses the damaged areas through any available pores, cracks, and voids, and then interacts with alkali, sulfates, and other chemicals naturally present in the pore water solution. The interaction of these different chemicals creates a hydrogel that changes the geometry of the crack, and over time, this hydrogel develops into the backbone of concrete strength, that calcium silicate hydrate. And that's the key. It's not that we're just changing the geometry. It's a material that we're changing the geometry with. It has a chemical interaction with the crack as well as the empty space of the crack to create that bridging material that functionalizes the interfacial zone. Now, this is done between the pore water solution, the crack surface, the crack subsurface that leads to the concrete body. Now, this dense mass of newly formed hydrogel bridges cracks and voids that reduce the localized stress from the applied loads, which is the root cause of concrete crack propagation and premature failure. Now, the primary impact of this hydrogel is to alter the geometry and the material properties at the crack site. Now, looking at that equation again, our aim is to reduce the crack length, A, and strengthen both that crack, that bridging material, and the plastic zone so that it goes from having plastic properties, deforming and not being able to go back to its original shape, to having more elastic properties, which in our elastic zone, it has a greater modulus of resiliency, meaning that when we remove those forces elastically, it will be able to deform back to its original shape. Now, the stress distribution changes from being perpendicular to a crack to a more radial direction, which in essence blunts the crack tip. This blunting action significantly reduces the energy to drive crack propagation, thereby stabilizing the crack and preventing further deterioration of the concrete. Now, for my technical enthusiasts among us, it's fascinating to note that the efficiency of crack blunting by hydrogel depends on several factors, including the chemical cross-linking density of the hydrogel, which determines its bridging and strengthening capacity, the placement and distribution of hydrogels within the deteriorated concrete, and environmental conditions, particularly the presence of moisture, which activates the bridging and strengthening behavior of hydrogels. And something else is the folks who are applying it. That's why it's important to note that Not all hydrogels are created equal. And while I'm trying to generalize this discussion, you're not going to get the same value added performance from every hydrogel that's out there. All right, to summarize, this preparation was geared to prepare the audience for a detailed explanation of this advanced solution, indicating that a baseline knowledge of the subject matter was expected. Now, the approach taken in the presentation is akin to jumping straight into an advanced topic in physics, assuming the audience has already familiarized themselves with the basics. This presentation explored an innovative approach to enhancing the durability and integrity of deteriorated and cracked concrete structures through the utilization of colloidal silica-based hydrogel. The presentation was structured first, define the overarching purpose and primary objectives, which were focused on addressing and mitigating the issue of cracked propagation in concrete, a prevalent challenge that significantly undermines the structural stability and lifespan of our national infrastructure. The foundational segment of the presentation dove into the mechanics behind crack propagation in concrete structures, establishing a critical understanding necessary for grasping subsequent solutions presented. This section was designed to set the stage for the introduction of a groundbreaking method in the realm of crack repair and maintenance. The key highlight of the presentation was the discussion on crack blunting with hydrogels, colloidal silica-based hydrogels. This segment unveiled the chemical and physical interactions between colloidal silica-based hydrogels and the internal surfaces of concrete cracks, as well as with the pore water solution present within concrete. The narrative and illustrations were designed to explain how hydrogels not only bridge the cracks, but also modify the crack's geometry and alter the stress distribution patterns that typically lead to further crack propagation. The purpose of employing colloidal silica-based hydrogels, hence, is underscored as a strategic intervention to blunt the cracks, effectively enhancing the structural integrity and extending the lifespan of concrete structures. This discussion emphasized the understanding of the mechanics of materials and material science, crucial for comprehending the effectiveness of hydrogels in concrete repair. In summary, the aim was to elucidate a sophisticated yet profoundly impactful technique of using colloidal silica-based hydrogels to counteract crack propagation in concrete, promising a significant leap forward in the field of structural engineering and maintenance. In conclusion, hydrogels present a pioneering approach to concrete repair, offering a viable solution to the perennial problem of crack propagation. By creating a crack blunting phenomena, hydrogels not only extend the surface life of concrete structures, but also contribute to more sustainable infrastructure management practices. Thank you for your attention, and I welcome any questions or discussions about this innovative methodology for concrete repair.